This is part 2 of the simulation series, and part 1 focused on the latest methods of how we simulate magnetic resonance systems in general. So this part 2 will be about the practicalities of, which button do you press, which command do you give, which parameters do you need to supply, and where do you stick them, and such like. There are 2 principal messages, I'd say, that I hope you would take away from this lecture. A is this quote from 1860, when members of UK Parliament asked Charles Babbage, the early mechanical computer pioneer, what would happen if they put wrong numbers into his mechanical computer. Well, of course, only wrong answers can ever come out, so garbage in, garbage out. That's the first thing about simulations that one must bear in mind. And the second thing is the answer to the question that I often hear, right, as the man who maintains SPINACH documentation and such, like, can SPINACH simulate this? Can SPINACH simulate that? Can it simulate DNP? Well, the good news is yes, it can. And the slightly longer story is that, of course, it depends on which DNP you are doing, under what conditions, under which pulse sequence, in liquid, in solid, under magic angle spinning, and so on. So the good news is there's now software, including SPINACH, that can simulate all forms of DNP, as you will see, including the forms that haven't even been analytically analyzed yet. But the bad news is that the efficiency of such calculations, the time it takes to simulate, it depends rather strongly on what it is you are simulating. It is nearly instantaneous and highly accurate in liquids, and it is excruciatingly slow and not terribly accurate in spinning powders. So we will go through the whole thing today, at least superficially, which numbers do you enter into which section, and I will comment as we go along about the complexities as well. Okay, so the reminder, we had this slide in the previous lecture, which I encourage you to view, what happens inside a computer when you are telling it to simulate a spin system, an NMR, EPR, DNP, whatever it is. We must specify the spin system, what is coupled to what and how, the type of the instrument, things like the magnetic fields, the strength of the radio frequency, microwave fields, and so on. And, well, roughly speaking, the pulse sequence, which experiment we are doing, in what sequence the pulses are given, in which phases, and so on. Then, ideally, in the perfect world, the software itself generates the spin Hamiltonian. It uses it to find the thermal equilibrium, and for DNP this really matters. And then it builds the relaxation super operator, because that's the other thing that really matters in relaxation-driven experiments. It merges the two, so corrects the super operator for the thermal equilibrium. It builds the time evolution operator, it's called the propagator, and it creates the system trajectory as a function of time, what is the wave function, the density matrix, whatever it is that we use to specify the spin system. And then we calculate the observables. Now, once again, the good news, if you are using SPINACH, the only thing you would need to do manually is this first stage. You need to specify the parameters of the system and the instrument. Of course, the bad news is there's rather a lot of those parameters to specify. And I've posted a couple more tutorials to Dropbox. I'll put this link into the chat window after the lecture, or take a screenshot or something like that. There are a few more step-by-step classroom level tutorials of various types of magnetic resonance simulations on this link. Okay, so what do you need to provide? Roughly speaking, you need to tell the program what your system is, which means specifying everything that goes into the Hamiltonian. Well, I've listed everything here, and the first term in this great big complicated sum are the Zeeman interactions, roughly the magnet, the chemical shielding for the nuclei, the G-tensor for the electrons, and such like. And the general strategy for you finding all these parameters is you should get hold of your nearest chemist and just shake them until they give you those parameters. Nice and easy. If there's no chemist around to shake, Then typically chemical shielding tensors would be there in the literature. Be careful, there's a difference between chemical shielding and the chemical shift. You can look it up. And then G tensors for the electrons. If there's no experimental data available, generally speaking, if it's a CHNO molecule, they can be computed reasonably easily with quantum chemistry packages. Talk to your quantum chemists, they will do that to you and for you. And then that's an example. These are chemical shielding tensors in strychnine, I think. So you can see carbon atoms are shielded slightly anisotropically, more anisotropically in aromatic systems. But these are, ellipsoids, just different directions in space. They're shielded differently. And SPINACH will tell you, the documentation will tell you, and I will tell you in a few slides how to supply that information. And internally, SPINACH builds the spin Hamiltonian, so magnetic field. That's G tensor proportional to G tensor, and that's the electron spin operators. Excuse me. Again, magnetic field, Zeeman tensors for the nuclear spin operators, and so on. And typically straightforward DFT is sufficient if you are working with a diamagnetic CHNO molecule. As the molecule gets bigger, particularly for things like lanthanides and such, the level of skill is increased. So let's say if it's a closed shell molecule, just use the off-the-shelf software. If it's open shell, or God forbid it's a lanthanide, then talk to quantum chemists. They would know how to do it. Okay, so the next thing is internuclear interactions, how the nuclei are coupled, and quadrupolar couplings. That is because some nuclei are not spherical and they sense the electric field gradients. So J couplings and QIs, internuclear dipolar interactions, normally either literature or DFT for J couplings and quadrupolar interactions. Nuclei, for all intents and purposes, are point particles for us in spin dynamics. And so dipole-dipole interactions can just be extracted from Cartesian coordinates. So if you supply the X, Y, Z to SPINACH, it is smart enough to figure out the dipolar tensors and integrate them appropriately. And that's the horrible Hamiltonian that it builds internally. So the J coupling, although it's called scalar coupling in the literature, strictly speaking, it's actually a tensor, but the anisotropy rarely matters. Then the quadrupolar interaction that looks like a quadratic coupling between the spin and itself for various reasons that I think I will talk about in a couple of weeks' time. And that's the dipole tensor. The next thing is electron-nuclear interactions, so the hyperfine coupling. It has two mathematically different components, although they come from the same physics, they're mathematically different. One is isotropic, so-called Fermi contact interaction, and the other is anisotropic, and that's mostly the dipolar interaction. Once again, you get them mostly from the literature or from DFT, and this is where electronic structure theory gets a bit more complicated. You see the real wave functions, they have a cusp at the nucleus, so the little sharp spike. But Gaussian basis sets commonly used, the top of the Gaussian is smooth. And so standard basis sets would underestimate Fermi contact interactions. You need dedicated basis sets like EPR 2 and 3 from Vincenzo Barone and company. The Hamiltonian is fairly small. Once again, the program builds it for you. Notice that the hyperfine tensors can be strongly directional. This is pyrene cation radical, and it's almost needle-like in this ellipsoid representation. So there's almost nothing perpendicularly to the benzene rings, but a lot, nothing parallel, but a lot perpendicular. And also notice that anisotropic hyperfine coupling and electron-nuclear dipolar coupling is actually more or less the same thing. So don't specify both the coordinates and the hyperfine because it will count them twice. Then the really difficult part are the inter-electron interactions, because these are rarely known and really hard to measure. You have to fit complicated EPR spectra, exchange coupling, zero field splitting, and inter-electron dipolar. Horribly complicated Hamiltonian, and the practical accuracy of DFT, don't even think about it. DFT fails dramatically for these interactions. You really need highly sophisticated electronic structure theory packages like ORCA, and I would encourage you to read Frank Nez's entire back archive on how to compute inter-electron interactions, because this is seriously hard. That is, if you have a biradical in your DNP simulation and you want to know the exchange coupling, go talk to very serious specialist quantum chemists who are specializing specifically in magnetic properties, because that is quite tough. Okay, and then microwave and radio frequency, it's the pulses and your microwaves. From just the diagram of the probe, you will see at what angle it spins and what the geometry of the coil is. Then you know the geometry, you know the direction of the various magnetic fields. And once again, you give SPINACH the directions, I'll tell you how, and then it builds the necessary Hamiltonians. And notice that in many probes, the direction of the applied B1 field, unlike liquid state NMR, in solids, it's actually not perpendicular to B0. It's at some angle, and in many cases it matters. And the same applies to microwaves. So this is the probe from Bob Tico group, I think, and you can see the microwave channel here is coming at a certain angle, and so there will be certain geometric considerations to take into account here as well. Okay, so all of this, assuming you got it somehow, how do you enter it into SPINACH? SPINACH is a MATLAB package, and the entry points are basically MATLAB structures. If you've ever written a Hello World program in MATLAB, it's not much harder than that. There's the first variable, it's called sys. That's a general system specification, what the magnet is, what the isotopes are, what the labels are, various output files, level of printing, algorithmic options if you're an advanced user, etc. But basically something like that. Magnet field, cis.magnet, that's an X-band EPR magnet, cis.isotopes, electron, nitrogen 14, fluorine 19, and 4 protons. So this is all extensively documented on the website and in a few published papers with the tutorials. So read through the manual or look at the example set, about 100 examples there. Just edit something that's already there, and this is how you specify it. Then the next important thing is the basis field, and this is simulation formalism, symmetry, basis sets, conservation laws, and other such things. Now, levels of difficulty here vary, depends on how advanced you are. That's an example. So formalism, spherical tensor basis in Liouville space, no approximations, and we have two groups of symmetry equivalent spins. So S2, it's a permutation group of two items, spin 4 and spin 5, spin 6 and spin 7. So this roughly tells SPINACH how you would like to simulate that in Hilbert space, in Liouville space, whether you would like to take any symmetries into account, whether you would like to impose any coherence level filters and such like. There's plenty of further options in there, but all documented, and you can see human readable. And then inter, these are all the interactions. This is what we have just talked about. You have it scribbled on paper somewhere, but there is a standard syntax that enters those parameters into SPINACH. So inter Zeeman eigenvalues, so for the electron here, so particle number 1, and you can see the eigenvalues of the G tensor here. And then you specify the Euler angles as well. I think it's in the next page somewhere. And then inter is also responsible for relaxation series, in this case, Redfield series, so we are in a liquid. To keep the secular terms, specialists will know what it is, Redfield kite at high field, and the rotational correlation time of 80 picoseconds in this case. That's the continuation of the same thing. So you can see eigenvalues of, in this case, hyperfine tensor, I think, yeah, intercoupling eigs. Then some space is made for Euler angles, but they are not specified because they're assumed to be 0 in this case. And then what do we do next? So these are just variables. They are MATLAB variables like you would enter any other MATLAB variables. SPINACH needs to be told about this. So we need to launch a function that really gets SPINACH started, because here we were just assigning some variables. And the first command that gets things going is create. And what this does is it reads everything that you have supplied. It applies fairly extensive validation, so don't expect it to be happy on the first attempt. It will usually tell you something like, oh, the number of hyperfine couplings you've specified doesn't match the number of nuclei. So of course, it doesn't have any physical insight, but it has topological insight. So if the number of Cartesian coordinate strings is not equal to the number of atoms, well, clearly something's wrong, right? And so it will stop and tell you quite often saying, hey, user, is there a typo over there? Or like this parameter is like the wrong order of magnitude by 10 orders of magnitude. So can you check that? So a lot of validation and a lot of printing to MATLAB console will happen at this point. And then what it also needs to do is it internally needs to decide the basis set, because everything is a matrix representation. So it needs to decide, you know, what is alpha, what is beta, what is alpha beta plus beta alpha. It needs to build the basis descriptor. It's much more complicated than alpha and beta. Of course, internally, it's irreducible spherical tensors, but that is actually pretty well hidden at the level of the starting user. You wouldn't see much of that. So we call this basis. And again, it will print a lot of diagnostics to the console about what it just did, what kind of symmetry it has applied, what kind of conservation laws it is assuming. It's always useful to read that output. It's a bit like any quantum chemistry package. And then another important thing is the assume command. You see, magnetic resonance is huge. Some people who are using SPINACH are running cryogenic magnetometry on dysprosium clusters with, you know, exchange couplings in the inverse centimeters and some horrible magnetic field sweep in the time domain. And somebody else is running metabolic MRI, which is, you know, for all intents and purposes, just an isotropic J-coupled system at high field. So the rotating frame transformations, the interaction representations, relaxation theory assumptions, what you can and cannot ignore, circularity, blah, 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 differs wildly between different types of magnetic resonance spectroscopy. And the reason this command exists is, of course, the kernel of SPINACH is just an algebraic engine. It doesn't need to know. We need to interface it to physical reality. And then if you look inside this function, SPINACH is open source. If you just look at the annotated code, you will see a great long list of all the special cases in magnetic resonance. Like if it's EPR spectroscopy, okay, keep all the secular couplings between the electrons, but make them pseudo-secular between electrons and nuclei, but make them strong between the nuclei because nuclei are still sitting in the laboratory frame, that sort of thing. So it attaches tags to every interaction you have supplied, that when you request the Hamiltonian, correct approximations are being applied to every operator that goes into that Hamiltonian that are specific to your instance of the spectroscopy that you are doing. In this particular case, the instruction is given to just ignore all approximations, completely not apply anything, and just return the full laboratory frame Hamiltonian if we ask for one. It's not very often that such assumptions need to be made, but that's basically a command to not make any assumptions. If we did an NMR spectroscopy, it would have said NMR. So once again, details in the manual. And then the roads diverge. On the one hand, SPINACH is written to service a sizable community of super experts, like of the people at the cutting edge of the development of the magnetic resonance itself, who would need every little nitty-gritty and every individual operator. On the other hand, there are hundreds of pre-programmed experiments and pulse sequences that are easy to use for somebody who is not an experienced spectroscopist and is simply modifying some example. And so there are low-level functions in SPINACH and there are high-level functions in SPINACH. If you are a specialist, you would need these low-level ones. So there's a command called Hamiltonian, returns you the Hamiltonian operator or super operator or the rotational basis, for example. Relaxation returns you the relaxation super operator, depending on which options you supplied. Equilibrium is the thermal equilibrium. Then operator, depending on what you ask, returns you individual operators or individual spins. State returns you individual states. In Hilbert space, they're the same as operators, but in Liouville space, they're not. So there will be vectors that you will be given. Average Hamiltonian theory, evolution, time evolution, and so on. Once again, a couple of hundred functions by now. So these are low-level functions. They are for the folks who are designing magnetic resonance, because they need to operate at this most fundamental level with individual bits and pieces, which then they know how to put together. There's also the user end interface, where all of this complexity is hidden and the pulse sequence is pre-programmed. Like you say, okay, Spinach, I want a cozy, and press the button, and it'll say, okay, but okay, what's the sweep width, and so on. And as soon as you supply all the reasonable things that you would tell a spectrometer, it will run you a cozy and not ask too many questions. So let me give you a practical example, and this is a recent paper that we published with the big group of NMR spectroscopists in Boston. So at some point, Harry Arsenari and Andras have, I think we just met at a Euromar in Aarhus, I think it was. And they had this fluorotyrosine, a molecule which was intimately familiar to me because I wrote a PhD thesis on it. On the hyperpolarization. But they were looking at an entirely different aspect of it. They said, Ilya, they said, you know, this usual TROSY thing between nitrogen and proton, where the CSA relaxation sometimes delicately compensates the dipolar relaxation, and the lines are really narrow. Harry said, we suspect that something a lot more dramatic, but kind of similar happens between this carbon here and this fluorine there. They said, can you generate the relaxation superoperator and analyze it? This is a much harder problem than nitrogen proton because there are two CSA tensors here, both very significant. So you have not just DD-CSA cross-correlation, you have CSA-CSA1, and you know the equations explode to the size beyond most people's pencil work capabilities. And if you compute the shielding tensors, you can see that the fluorine is very strongly shielded, as it should be. And then there's this carbon, and there's also the dipole interaction that is worked out from the coordinates. And Spinach by then was able to directly import Gaussian logs, so quantum chemistry calculations can just be read in automatically. So we read them in. Once you get the data in, it's exactly the same flow chart that I've just shown you. In general, we said cis.isotopes is fluorine and carbon, inter-Zeeman matrix, a cell array of two matrices. The first matrix is what came out of DFT for the 8th atom. So in a quantum chemistry calculation, it was atom number 8. Now it's atom number 1. Carbon was atom number 7. Now it's atom number 2. Then coordinates, again, we lifted the Cartesian coordinates from the DFT import. And standard Redfield relaxation theory, Spinach automatically accounts for all syncable cross-correlations in there. We want relaxation rates, so laboratory frame. No worries about the equilibrium destination because we just want the rates. And 25 nanoseconds is typical for a pretty large protein. And this was Harry's genius guess. He suspected that for very large proteins, this is still going to work, even though fluorine is normally inapplicable. Fluorine and NMR lines get too broad too quickly. Then no approximations, Liouville space, spherical tensors, and we call create, and then we call basis. And it's literally just a meta of, I think it's a quote from Game of Thrones that I've read the book and followed the instructions. So read the wiki, follow the instructions, you'll be fine. Okay, now this is a very beautiful line because this one line contains, I would say, about a dozen papers by now. So I've started writing when I was in Oxford. You can see that the paper about large scale calculations of Redfield relaxation superoperators. It's but at the level of the user, you just say, okay, R equals relaxation of the spin system, and it returns user relaxation superoperator. And then we just want the elements of it. Right? We want that relaxation rate, this relaxation rate, between various states. And for that, we need to get those states out. And well, we just ask Spinach. FP is a state of the spin system, L plus on the first spin. First spin is fluorine, so this is going to be F plus, the raising operator. F minus is the state of the spin system, L minus on the first spin. Fz is the state of the spin system, Lz on the first spin. And then we don't want the F plus and the F minus, we want Fx and Fy. And so in this case, Fy is F plus minus F minus divided by 2i. So any one of you who has ever written a spin operator and computed a commutator with a pencil would remember these standard relations between spin operators. The same for carbon, the same for various multi-spin orders that you need for TROSY to work. Normalization, you are calculating an element of a matrix. The vectors have to be normalized. And I would remind you that if we want an n-case element of matrix A, it's a scalar product, n-a-k. The vectors must be normalized, and then you get the n-case element of it. In our case, the 1 over T1 would be the element corresponding to Fz. 1 over T2 would be the element corresponding to Fy. So we only need a few specific elements, even though the relaxation superoperator is fairly huge. And then we just print them, right? So this is Cz transpose relaxation Cz. So it's an element, the matrix element corresponding to Cz and Cy. And then you print it. And this is a fairly standard TROSY plot. So that is the left line, that is the right line of the multiplet, and that is just the transverse spin order. And as you can see, the left line is really broad, the center somewhere in the middle, the multiplet as a whole, and then the right line is really, really quite narrow. Think about it, this is 25 nanoseconds, so a large protein. This is fluorine. Normally, if you were doing straight aromatic fluorine spectroscopy, the line width would be in the kilohertz. And this is less than 10 hertz. So I don't know how Hore came up with this idea. It was a brilliant idea. And so then, after a couple of days of calculations, we see exactly what's happening there. And then the rest of the Boston group, there's a very, very long list of courses in here. I would advise you to read that paper to see the details. Ran the actual spectroscopy, and indeed there are extremely sharp or extraordinarily sharp lines here under conditions where the line widths are typically in the kilohertz. So that's a fairly typical calculation. You plonk the system parameters in this case we read them from the DFT calculation. And as you can see, there's a certain need to know what you're doing. In that, at least you need to know what the relaxation superoperator is and enough linear algebra to know how to extract an element out of a matrix, no way around it. But at least we have spared the end users the really horrendous relaxation theory in this case, because that is really difficult. So SPINACH just returns you the matrix, and then you do with it what you will. Okay, so an example of a pulse sequence. So this was relaxation analysis. Let's take a look at how one would write a free-form, just wild pulse sequence if you are developing a new one. In pretty much the same way as you would write a pulse sequence for a Varian instrument. Now, after 20 years of doing NMR, I still can't program a Bruker spectrometer. I mean, oh goodness, that assembly language is killing me. But Varian, may it rest in peace, had actually a pretty sensible pulse programming language. It was a dialect of C. And what you'll see here is a dialect of MATLAB. Substantially, this is MATLAB programming, but with a lot of functionality that's already been implemented. Okay, so as I already mentioned, spin system assume NMR. SPINACH runs a lot of internal heuristics on the interactions. If it's a carbon coupled to a proton, make it weak. If it's a carbon coupled to a carbon, make it strong J coupling, and blah, blah, blah. And then we build a Hamiltonian, and we build the relaxation superoperator, and that it's dissipative, so it has to have an I in front when you make the composite Liouvillean, and that's just a matrix. It's a MATLAB matrix. You can do with it what you like. You can print it. You can extract elements out of it. You can exponentiate it. Do things with it. Then initial state. Typically, calculations begin on the z-axis in NMR. Okay, rho is a state of the spin system Lz on the protons. Then detection state, normally transverse, usually quadrature, so Lx plus I Ly, or equivalently L plus. Is a bit of a philosophical meta here on we are detecting on a non-Hermitian operators. The philosophers will get their knickers in a twist about this, but well, we can. So coil is L plus on the protons, proton coil idealized. Pulse operators, again, L plus, L minus, and put them together to make an LX. And then we apply the pulse. Right? I think for variant spectrometry, it just said pulse, and then lots of parameters in brackets. Here it says step because it's one time step under a fixed Hamiltonian. And in this case, step of the spin system under LX from the initial state rho for a duration pi/2. So standard excitation pulse in nuclear magnetic resonance, idealized as a different command if you want a shaped pulse. Then if we want to tidy up the mess, for example, if it's a part of a bigger sequence, a coherence order filter, in a spectrometer, you would need to make a phase cycle. That's a long story, but in a simulation, of course, we have direct access to the state. And if we don't like a particular coherence, we can just zero it out. And so coherence filters in SPINACH, of course, you can do a pulse, a phase cycle if you want to, but we can simply just erase the coherences we don't want. So rho is a coherence of the spin system under this state rho. So we're overwriting this state. Keep coherence level 1 on the protons and just wipe everything else out. So, and then, for example, run the evolution. Evolution of the spin system under this Liouvillean L, with detection on that coil state from the initial condition that came out of our pulse and the coherence filter, with a time step of 0.1 millisecond for 1,000 steps, and return the observable corresponding to this coil, write it a variable, MATLAB variable called answer. So you can see it's a language, it's just a programming language. It's a magnetic resonance programming language. And there's a horrendous amount of mathematics that went into every single function we are calling here. If you open Hamiltonian.m and look at the source code, years of programming that was, but it's now tidied up, packaged up, and it's just dialect of MATLAB. Now, what is important about all of these functions is that many of them automatically parallelize, and many of them automatically use GPUs. If you enable GPU processing as a switch, you can find it in the manual what the exact syntax is. But if you have a fancy NVIDIA graphics card, MATLAB supports GPUs automatically, and by extension, so does SPINACH. We've programmed a few specific GPU routes for efficiency. Really helps with things like magic angle spinning, DNP. Things get a lot faster. And the bigger the spin system, the bigger the difference as well. So all of this, when you look at this code, put a mouse on it, press Ctrl+D, MATLAB automatically opens the source code of that function. You will see the instructions for use in the header. Everything's documented, everything's commented, and everything's on that wiki as well. Okay, now, assuming we are a user, right, not a specialist, we're a user not who just needs to get a spectrum simulated and isn't particularly interested in all the nitty-gritty. And these contexts are our way of hiding all of the complexity. So let's look at this. So this is a simulation of a cross-polarization experiment, some magic angle spinning CP, and it's got a certain syntax. And here spin system is that spin system data. Remember, we called create and basis. Cross-pol is the pulse sequence name. It's one of the pre-programmed black boxes inside SPINACH. So if you just want like a proton to carbon cross-polarization experiment, you just call it. And you will need to supply a few parameters. It will tell you what the parameters are, spinning rate, the amplitude of the RF on the proton and the carbon, and the assumption set is NMR. And single rot here refers to a context of single axis rotation. It's a fairly complicated combination of assumptions, settings, and internal algebra. You have to set up a calculation in a certain way for magic angle spinning in all the directions and all the axes and whatnot. But in the end, this command will simply spit out a free induction decay, which as an experimentalist, you understand. You can Fourier transform it and get the spectrum. You can apodize it. You can export and process it elsewhere and so on. So this is kind of packaged up into the sort of call that an inexperienced or a disinterested user can simply just call. And then the important structure here is parameters. And there you need to tell it a few things. Firstly, of course, the spinning rate. It's a big difference between 10 kilohertz and 100 kilohertz. Then the spinning axis. SPINACH supports magic angle spinning, but also spinning around any other axis. You can spin perpendicularly if you like. And then it's a Fokker-Planck theory in there, but to a good approximation for single rotation, it's the same as the Flaquet theory. So this is, roughly speaking, the number of discretization points in the rotor phase grid. So how many points we've got to digitize our spinning rotor. The bigger the better, really, just increase until the answer stops changing. And then further parameters, irradiation powers, what the amount, the strength of your radio frequency field is in terms of notation frequencies on proton and the nitrogen 15. And then what is the phase of that irradiation? So we irradiate on HY and NX. And then the initial excitation operators, the one that we use for 90 degrees pulse in a cross-polarization experiment, are HX and Y. So you can see there's nothing here beyond what you would have told an NMR spectrometer. So it's exactly the same parameters that you need to know if you perform an NMR experiment, just entered into MATLAB in a slightly different way. And those tutorials that I've linked, the Dropbox link, they contain a step-by-step walkthrough through solid-state NMR simulations of this kind. And then a few other things. Of course, coil in an NMR instrument, you would actually have a coax cable that you would, click in somewhere. To SPINACH, you have to tell that that's an L+ operator on nitrogen 15, corresponding to the N15 detection. The number of steps, so 100 time steps, and each time step is 10 microseconds long. And then the spherical grid, so it's alpha and beta spherical grid, 100 points, full sphere. That's a repulsion grid from the old paper from Niels Christian Nielsen's group. So again, if you're a solid-state NMR spectroscopist, you would hopefully remember what these spherical grids are. And verbose tells SPINACH to print an awful lot of diagnostics. So there are other contexts. There are liquid, powder, crystal, rod map. This is a carefully controlled positioned crystal. Double rotation for double rotation probes, and imaging. This is for diffusion flow, hydrodynamics, and other things to do with MRI. Okay, so let me give you an example of a pretty straightforward simulation of a nosy on ubiquitin. We have import from PDB and BMRB, so there's a command called protein, which simply populates this cis and inter. Your protein will be different, but you would need, of course, a BMRB file for it with the chemical shifts for everything. J-couplings are guessed at the moment in a monstrous database. You can look into the database and set your own J-couplings. But magnet 21 Tesla, these are tolerances. It tells SPINACH to ignore distances above 4 angstroms because we're doing a nosy here of a very large protein. It probably will be all right with 5 angstroms, just a bit slower. And to ignore all the J-couplings smaller than 2 Hertz in that calculation. You can decrease this cutoff, but the calculation will get a bit longer. Then Redfield relaxation theory, all the secular stuff, 5 nanoseconds, fairly typical for ubiquitin for the rotational correlation time. A specialized basis set, that was the topic of my previous lecture of what this is. I will not discuss this here. And then exactly the same syntax. Create the spin system from this system and the interactions that we've read from PDB and BMRB. Build the basis, set the parameters of a nosy sequence, mixing time, transmitter offset, sweep width, number of points to zero fill before the Fourier transform, the working spins, in this case protons, and the units of the axis. And then that's it. So we call the context called liquid, which sets up internally all the data structures required for liquid state NMR simulation, builds the associated pulse, detect, and so on operators. So that's our spin system. That's the pre-programmed nosy sequence. It's already there. These are the parameters, nothing beyond what you would have told the spectrometer. Assumption set NMR. And that was the first ever fully quantum mechanical simulation of a protein-sized spin system. I mentioned that in the previous lecture. This is a zoom into a tiny fragment of what is a huge NMR spectrum, and it's quantitatively correct. So fully quantum mechanical time domain magnetic resonance simulation with a full relaxation superoperator, including all the cross correlations. So that was our by now fairly well cited paper when we found low complexity algorithms for the simulations of this size. So it reduces what would have been a gazillion by a gazillion matrix to something that's vaguely manageable. And Dongheng Li has recorded extraordinary experimental data for us to compare against here. Okay, another example, this time zero field NMR. This was a collaboration with Thomas Theis from Duke University, I think he was at the time. Zero field methanol, so Dima Budkar style experiment. 3 protons and a carbon, so the CH3 groups. The magnet field in this case is 0. And these are the J couplings between those protons and the carbon. Now, in this case, no approximations because it's a tiny spin system. We can run it exact. And again, it's a pre-programmed pulse sequence. We give it the sweep widths, the number of points, the number of zero fields, frequency offset, which spins to work in axis units. And we don't want to invert the axis here because these are not ppm. And then the same exact syntax, create the spin system, and it will print you a pile of diagnostics for it. Basis set, and because the zero field pulse sequence is pre-programmed, once again FID equals liquid context. This is our spin system, this is our pre-programmed pulse sequence, these are the parameters, and here of course there is no magnet, which means no secular approximations, which means no rotating frame of any kind. And so here is one of those rare cases where we need to tell SPINACH, hey SPINACH, you are not allowed to ignore anything. You should include complete Hamiltonians for every interaction there is in this system. And that means lab frame. And that's just a reproduction of figure 1 from paper from Thomas's group. Okay, so that was liquid NMR. Let us now go to DNP. And this is where, you know, some kinds of DNP are really easy to simulate. Liquid state DNP, easy peasy, lemon squeeze. Solid state is much harder, particularly if it's spinning. So overhauser DNP in liquids, you know the drill. You just smack the electrons hard as you can and hope that a little bit of the magnetization drifts over to the nucleus through the overhauser effect. Now, because the magnetogyric ratios of proton and electron are opposite, electrons are actually polarized negatively in our basis set. So when we flip them, they're flipped into positive, and then they relax back into negative in the space of a millisecond or so. And then you can see a blip of the nuclear magnetization, which was previously positive, but goes strongly into negative as a result of this overhauser cross-polarization. These are absolute units of just the populations of the corresponding states in the basis set. So it works in liquids and in various very, very soft solids with lots of internal motions. Now in DNP, there are 2 recognized mechanisms and many more I would suspect that are still unseen. More or less, you scan the microwave frequency or you scan the field and hope for the best. If something happens, if there's some nuclear magnetization turning up, you try figuring out what it is. And some of it is called solid effect and some of it is cross effect, you know, for monoradicals, biradicals, and increasingly, I think, multi-radicals as well. That's an example when you are scanning microwaves, perhaps through a tunable gyrotron at a particular magnetic field. There will be resonance conditions, there will be strong positive proton magnetization, or a strong negative one, or some transient, extremely narrow matching conditions. I would encourage you to read a wonderful series of papers on the theory of all of that. So from Jonathan Hore, Akiva Fine to Shimon Vega on one side, and from Alex Karabanov and Walter Köckenberger on the other. In fact, it was collaboration with these fine gentlemen that got that simulation technology implemented into SPINACH. And then hopefully a phenomenon called thermal mixing emerges as a thermodynamic limit of all of this, plus the spin diffusion, plus all the mechanisms that are still unknown and being explored. Now, there are also chemical routes, as many of you will know. There is a really complicated and fancy technique called chemically induced. And although the three letters D and P are inherited here, it's a historical mistake. CADNP has nothing to do with DNP. It's actually a chemical reaction that sorts nuclear spins. It's because in radical reactions, the reaction probability depends on the spin state of the electrons, and then through the hyperfine coupling on the spin state of the nuclei. And so whether or not it's going to react depends on where the nuclei are pointing, and so you get a little bit of polarization as a result of that. But well, I've written a PhD thesis on this a long time ago. This is how it looks. You have an optical fiber, a little refreshing tube to refresh your sample, and a fairly complicated mixture of chemicals inside it. And there's also, of course, parahydrogenation, when you bubble parahydrogen with some catalyst. The kinetics of that is pretty complicated and it's still being developed, but it's just effectively magnetization pumping terms in the Liouville van Neumann equation. So we will not talk about this. SPINACH can do it, but this is not for today's lecture. So let us focus on DNP specifically. So starting with the simple things, liquid state, overhauser, DNP. Using that exact same syntax that I've already mentioned, you would say, okay, cis dot isotopes equal electron and a proton or a couple of protons, and then specify the coordinates or specify the hyperfine couplings. Call create, it will build the internal data structures and check your input. Call the basis, it will build all the basis sets and operators. Assumptions in this case are EPR, so inter-electron couplings, are secular electron-nuclear couplings, pseudo-secular internuclear couplings, strong. That's the rotating frame that is specific to high-field DPR spectroscopy. And it's the same, flip the electron into positive, it relaxes, and then the nuclei, depending on the distance, have these blips. So, initial condition, equilibrium. Rho equals equilibrium of the spin system. Kilometer of mathematics takes place internally. It just returns you the vector, which is your equilibrium, thermal equilibrium state vector at your temperature. Detection state, we want longitudinal magnetization on the electron and both protons. So we specify 3 different coils here. LZ on spin 1, 2, 3, so 2 nuclei and the proton in this case. Get the Hamiltonian, get the relaxation super operator, get the electron pulse operator, make it into LX. Apply the pulse, so rho is a step of the spin system under LX, so electron pi, so flip the electron around. If you want a soft pulse, run a soft pulse function, it's in the manual. And then run the evolution for, in this case, about a millisecond, and this is what you will get out of it. Now, there are, I would say, no standard pulse sequences for DNP because everybody's running their own stuff, particularly with solid state DNP. Some people are decoupling the electron, other people are trying to do a complicated optimal control type sequence on the electron. So there will be a fairly complicated song and dance with, which pulses go where, how they are interspersed by the evolution periods, but substantially it's just a repetition of these little steps here. Give a pulse, run an evolution, give another pulse, run another evolution. And if your pulse is not perfect, there's a command called shaped pulse, which will give you a finite width and finite amplitude shaped pulse that will hopefully match better to what you do. Okay, so this is liquid, and liquids are easy, right? So SPINACH does all kinds of liquid state NMR, funnily enough, as you will see in the last slide, both known and unknown. But the solids are harder, and they are not harder because of the software. We can simulate any solid state DNP experiment easily enough. It's usually a fairly small spin system, and even if it's large, we've got ways of doing that. The problem here is chiefly that the spin system is just so badly defined. You would normally have a glass in DNP juice or whatever, which will have these molecules flash frozen in a distribution of orientations, but also distribution of conformations, because a lot of these radicals are floppy. So there will be distributions of where the hyperfine tensors are pointing, but also distribution of distances between the electrons and the nuclei and the nuclei. Then you've got the rotor period discretization if you are spinning it. Then there are distributions of, for example, zero field splitting parameters. So that's a distribution of D&E parameters in zero field splitting of gadolinium DOTA. And that's used sometimes for DNP. But you can see orientation distributions is 3 angles in a static solid. Distance distribution is another variable. Conformation distribution, goodness knows how many dihedral angles you've got in there. And then distributions of some internal parameters. And if we start counting dimensions, we are talking 6, 7, 8 dimensional distributions. And if you've got 10 points in every dimension, that's 10 to the 8th, right? 10 million, 100 million, game over, right? So the problem is hard, not so much because the spin dynamics is hard. It isn't. The problem is hard because the system is horribly badly defined. And it gets really quite serious. I was on the one, I really laughed when this paper came out from Santa Barbara group, where they pointed out that it has been observed that DNP-induced NMR single enhancement of nominally the same sample can vary between different experimental sessions, which to me sounds like different kind of freezing. So the crystallite size will depend on how quickly you froze the sample. Then the phonon statistics in the crystal or a glass will depend on how you froze it. The relaxation rates will depend on the phonon spectrum. And essentially solid state relaxation theory, it's getting better. Alessandra Lunghi in particular in Dublin is making a lot of progress with this. But still, I would say as of now, unless you've got a monstrous supercomputer, solid state relaxation theory doesn't properly exist. We have unknown phonon statistics. We have poorly understood internal motions, including quantum rotor effects and things like dipolar network dynamics, exponential complexity things in there. So we don't really have, in the same way as we do in liquids, a good relaxation theory. And then all the flash melting and transport with, all the melts and all the non-adiabaticity and all the turbulence that you have in there, and all the level crossings that you have to go through if you are transporting it from one magnet to another. So I would say, and there's a distribution of opinion as well. So if you read the recent papers from Fred, he is quite heroically battling all of this. So I think the latest paper he has written, he reasonably claims that he more or less samples all of this, or at least most of this, to a reasonable accuracy. All right, but I think Fred was running things for a month, not because of the individual spin system. It's very easy to simulate an individual spin system, but because you have to integrate over this monstrous array of distributions. In liquids, we were okay. We had Redfield series, so I'll just skip that. But in solids, okay, so how do we do relaxation theory in solids? How do you do relaxation theory when you have no idea how something relaxes? Mr. Lindblad to the rescue, a Nordic mathematician who has derived an interesting operator. It's called the Lindbladian. It's a generic form of what any relaxation superoperator must be in order to be a mathematically valid relaxation superoperator. There are certain requirements. And it's a generic form of it. And in a sense, Lindblad theory is a poor man's version of relaxation theory. When you don't know anything about your relaxation, you only vaguely know which operator is responsible, like L+, and you vaguely know the rate. You can put this together, and that will give you a defensible relaxation superoperator. So for example, for T1, T2, it's black boxed into SPINACH. It will build this horrendous array of operators if you give it the T1 and the T2. But this is really a gesture of inspiration. When we don't know anything about relaxation, we vaguely know that it's spin flip. Then of course L+ is what spin flip is, and L-, and then we can build a Lindbladian out of it and hope for the best. So it's a fudge, use it at your own risk. That having been said, I've seen people using it with great effect. It's actually surprisingly decent what comes out of it. Quite unsurprisingly, Szyman, Vega and company haven't been satisfied with that at all. So they have made it a bit more detailed. So they assigned individual operators that they assumed responsible for nuclear longitudinal and transverse relaxation, specific rates, did the same for the electrons, and from the insights that they had into internuclear and electronuclear spin dynamics, they saw it mostly flip-flops. And so they created a flip-flop operator and said, okay, that thing, we just assign it to be responsible with some empirical rates. And this is slightly more detailed than just Lindblad. There's a bit of physical insight that goes into it. And then you plonk that into the Lindblad framework, and you get a slightly more physically motivated relaxation superoperator. A similar effort around the same time from Alex Karabanov, Greg Kwiatkowski, and Walter Kirchenberger, where they analyzed the problem transition by transition and assigned individual rates based on individual transition operators. And for nuclei, they followed the same route as Shimon and company. So both of these theories are now implemented into SPINACH. It was a collaboration. I actually went to Weizmann Institute to talk to the chaps, and we published a few papers with Walter and company. So all of these things are now in there as black boxes, just specify relaxation theory, Nottingham, and those parameters, and it will just turn it on. Now, assuming you know these rates, how do you simulate it? Well, there are two ways. Firstly, if you are looking at the time dynamics, as people often do, you run it in the time domain. You put your Hamiltonian commutation, you put your relaxation, you put your matrix exponential. We discussed it in the previous lecture, and that's your trajectory. You project out nuclear magnetization, and that's your little blip and relaxation and such like. Alternatively, if you want the steady state, that is, let's say you say, okay, I'm going to be blasting it with microwaves for half an hour, and I'm not terribly interested in what transient states it goes through. I'm only interested in the final state. Well, remember that differential equation. It was d rho by dt equals minus ih rho plus r. Well, of course, in the steady state, d rho by dt is 0. That's the definition of the steady state. And so we put the derivatives that was here to 0. And at that point, a fairly nasty differential equation becomes a considerably less nasty algebraic equation for the steady state density matrix. And matrix inverse times a vector can be computed very efficiently. You don't need to invert, of course. There are methods like GMRes that compute this really rapidly. And then you get the steady state magnetization of your nuclei. SPINACH implements both this and this, depending on what it is that you are running. So steady state is actually significantly faster than doing the full time dynamics. And that's an example. So that, I think, is something that Björn Kartzelius asked us at some point to do, and we put it into the example set later. This is gadolinium with all the zero field splitting and other complications pertaining to that, with a swept magnetic field at a fixed microwave frequency. You can see there are matching conditions on every shoulder of the gadolinium EPR spectrum. And once again, fairly standard array of parameters. This is pre-programmed. Microwave power, microwave frequency, equilibrium state, detection state. So we want the LZ on some proton that's sitting next to the gadolinium. Microwave operator, electron sweep operator, right? The stuff that sweeps the magnet or the frequency. Spherical grid, and the fields, offsets from minus 80 millitesla to plus 80 millitesla around some center field here. And then answer equals powder, because it's a powder spin system. The pulse sequence is called DNP frequency scan. It's pre-programmed with these parameters. And there's a special assumption set for DNP, DNP exact that cuts no corners. In some cases where corners can be cut, there are other assumption sets. Alexander and Walter managed to simulate systems with thousands of spins using Krylov-Bogoliubov average Hamiltonian series. So there are extra parameters in that case, again, all documented, and the function is called solid effect, and it computes time traces for solid effect really efficiently as a result. Okay, so what about magic angle spinning? So we are, I think that's a couple more slides left, and that's it. We tried a lot, and I understand Fred has tried a lot independently. I think he's sort of got his own Frankenstein package that is a little bit SPINACH, and the rest is Fred's internal effort. He contributes some code every now and then to SPINACH, so it's like a mixed effort in this case. But I think the conclusion from both Fred and us is that there's at the moment no better way than the brute force. And if you implement it in MATLAB, well, it runs. If you really carefully program it, as Michael Wistort did in spin evolution, in really close to metal, almost assembly code efficiency, then it runs a little bit faster. But at the moment, there's in the situation when Landau's inner approximation is not applicable, there's no other way than the brute force, which means that you actually scan the rotor period. In this case, I think that's 2 electrons and the nucleus, and the rotor period is 80 milliseconds, and these are the energy levels, in the hundreds of gigahertz, minus hundreds of gigahertz, and then this. And these levels cross around, and if you read Fred's papers and also papers from Pera's group, there's a lot of sophisticated dynamics happening at these crossings. Some of them can be treated as anti-crossings if you're lucky, others cannot. But the only really surefire way to do it is to solve the equation explicitly in the time domain. Then you need a couple of thousand, 6,000 points in this case, in the rotor discretization grid several times to reach this steady state. And these are energy level populations as a function of time. And you can see at every crossing of these energy levels, there are fairly sharp and rather eventful, this is lengthy ring down in here, particularly here, processes. So in our latest papers from Fred, he samples these dynamics really carefully and efficiently, but these are really difficult calculations. Even, for a 3, 4, 5, we can probably survive a 10-spin system, but these are hours and sometimes weeks if you have to average over all those distributions that I've mentioned of calculations. All of this, so all of these pictures that I'm showing you, they are in the standard example set, which is supplied with SPINACH, all well documented. So I would say this efficient magic angle spinning DNP is at the moment about the brink of what the largest supercomputers can do if you try hard enough, chiefly because of such a grand averaging over so many different things. And finally, the last slide, and this is something that actually SPINACH enabled. At some point, Lucio Friedman found me and Maria Grazia Concilio at another Euramar and said, well, hey, folks, he said he was guessing that there may be some complicated dynamics in multi-electron systems that circumvent the standard problems that overhauser DNP has at high field. Now, those of you who work with solids, you don't have these problems, but the liquid folks are painfully aware of this little term here. Notice there's the square of the electron frequency in the denominator. That's a monstrous number. And at any reasonably high magnetic field, this denominator and that denominator just dominate the entire equation, and this is negligibly small. So at high field, overhauser DNP just dies. At 600 megahertz standard magnet, no way. However, the implementation of relaxation theory in SPINACH is extremely general. I've already mentioned that it does that integral by brute force. It doesn't even rely on the Zeeman frame. If your dominant Hamiltonian isn't Zeeman, it will still do it. It will even blink. And so Maria Grazia followed on Lucio's guess. I don't know how he knew it. He evidently knew it or had a suspicion. Anyway, she found strange, stray, unexpected matching conditions. Away from all the other matching conditions, at very high field that had pretty decent DNP, like a factor of 10, unheard of for overhauser DNP. And that was an interesting situation because we made these calculations and we ran them, Maria Grazia and I, and then Lucio says, well, okay, so what's happening? We say, we have no idea. And so after a couple of months of running post-mortem analysis on those calculations, a fairly elaborate mechanism turns up, which just got published in JMR. So lattice, right, our spatial degrees of freedom, they return electrons to thermal equilibrium. And then, as you know, microwave irradiation and also exchange coupling between two electrons in a 2-electron 1 nuclear system, they populate two spin orders. So this EZ, EZ, or the transverse ones. Now, overhauser effect ignores all the cross correlations. Roughly speaking, it ignores the EPR version of atrosy. And there's a ton of that stuff happening in EPR, very rarely explode. And so it turned out, after Maria and I did an awful lot of analytical and numerical relaxation theory, that there are cross-correlation processes between anisotropies of G-tensor and hyperfine tensor that convert these electron 2 spin orders into electron nuclear 3 spin orders in the same way as atrosy works. And then there's another cycle of microwaves and exchange couplings that gets us into a longitudinal 3-spin order, which then has another cross-correlation mechanism into NZ. Or alternatively, it's actually direct DD-CSA, because DD in EPR language is called hyperfine. So it's almost a atrosy-like mechanism from here to here as well. Anyway, turns out that there was a completely new and previously unheard of DNP mechanism that still works at high field, but you have to tune your spin system. So these are very narrowly specific, highly engineered spin systems. It remains to be seen if such systems can actually be synthesized. At the moment, it's a purely theoretical proposal. I understand Maria Grazia is working on it, but this is a situation where an entirely new phenomenon was first seen in a simulation, simply because the simulation has been implemented to treat absolutely everything. And then we've spent a considerable amount of time figuring out what the hell just happened in that simulation, and this complicated mechanism emerged. And actually, we've just submitted another paper with Maria and Lucio that I cannot talk about, but it's even more exciting than this. I think it will come out in a couple of days on Archive when Maria posts it in there. So that's my last slide. And this is where to look for further information. We published a lengthy tutorial, step by step, on how do you enter the spin system and how do you run SPINACH in MRC. So it's just a tutorial paper. There's this paper I've just talked about, which goes into some detail on how to set up SPINACH DNP calculations. I would also encourage you to read a recent paper from Fred Perez and Marek Pruski, who went large scale using a version of restricted state space approximation for magic angle DNP with great success. So I'm watching this with some hope, because they're using Monte Carlo to try and sample everything properly. And then also the recent papers from Fred Mentin, Shimon Vega group, and Walter Köckenberger group on solid-state DNP simulation. So at the moment, solid-state DNP, particularly MAS DNP, if you want to do it really accurately, it's at the edge of what you can just about do on a large computer, but it's slowly becoming possible, and SPINACH is one of the packages that can do it. Okay, that's me, and thank you for your attention.
Thank you very much for that really fantastic and thorough tour de force of what SPINACH can do. So we have a couple of questions. Please do keep adding questions in the Q&A box. We'll start with an anonymous attendee who asks, in EPR, strong dipolar and zero field splitting interactions are considered to be the same, but dipolar coupling is axisymmetric, but zero field splitting is asymmetric. And so what is the limit in which you should consider two strongly coupled spin halves as a spin one with a zero field splitting instead of a dipolar coupling?
Right. So in general, I would say, if in doubt about whether that approximation applies, simply run in the laboratory frame. So specify a pair of spins, and as strong an exchange coupling between them as you like, and as strong a dipolar. So long as you keep the calculation in the laboratory frame, it is by definition a correct calculation, because you are solving the exactly Will van Neuman's equation. If you do want to go into the rotating frame or some kind of interaction representation, then of course you need to worry about it. So in this, so you've got a number of questions like hidden in here, right? So strong dipolar versus ZFS. If you have two electrons with a spin half very close together, you know, to an extent that the clouds are overlapping, then in the individual spin representation, these are two electrons with a dipolar tensor. But you can choose, as you will know, to treat them in the total spin representation, at which point it's a singlet and a triplet, and the triplet would have a zero field splitting, or a term that mathematically looks like a zero field splitting. So in this case, there is really no sharp crossing point. If you can get away with this approximation, go ahead. If in doubt, simulate it in the laboratory frame. The problem with EPR, and it's often the case with lanthanides, right? If you have a dysprosium, right, those 3 or 4 electrons in there are so strongly coupled that, and it's for all intents and purposes a ZFS. But of course, a ZFS then pertains to a particular, you know, multiplet, and then there will be excited multiplets, and then it gets complicated. So if in doubt, run in the laboratory frame, and then you are guaranteed to be correct.
Okay, thank you. So we have another anonymous question, whether it's the same anonymous attendee or not, who asks, how is orientation averaging done for large anisotropic interactions in a non-spinning system?
Just a giant spherical grid. So you repeat the calculation, exactly the same calculation for a slightly different spatial orientation of the system. That can mean tens of thousands of calculations, unfortunately, particularly for DNP, because you are evolving under large interactions, which are in the megahertz, you know, for many seconds sometimes. This is one of the difficulties that Fred had to handle in his recent paper. So yes, unfortunately, it does mean thousands and tens of thousands individual little calculation. So having a huge cluster really helps, because you can parallelize it. SPINACH will parallelize across this number of nodes if you have a parallel MATLAB. There are various methods in EPR spectroscopy where you can sometimes do a field swept EPR spectrum by what's called a Voigtlander integrator. It's well implemented in EasySpin, where it's basically a giant analytical integral over the Fermi-Golden rule. But DNP being a time domain phenomenon, this isn't applicable to DNP. And so I'm afraid I'd have to give you the bad news. If it's a non-spinning system and you have to do orientation average for a DNP, that usually means north of 10,000 individual little calculations.
Okay. Great, thank you. Just had another question come through asking, how is electron-electron nuclear, so 3-spin overhauser effect, different from the 3-spin cross effect?
The difference is quite fundamental. The overhauser effect, the one that happens in liquids, is a relaxation effect. And the 2-electron to nucleus cross effect, it arises in the coherent Hamiltonian. So roughly speaking, if we choose to run the time backwards in our simulation, the overhauser DNP would continue accumulating in exactly the same direction. But in the negative time direction, the cross effect would completely undo itself. It would refocus. So cross effect is coherent evolution, and overhauser effect is relaxation. And there are 2 different parts of the equation of motion, right? Liquid state overhauser effect goes through the relaxation superoperator. So this is stochastic spectral power density of rotational diffusion driving your transitions. So it's the stochastic dynamics of the bath that does it. Whereas in the cross effect case, it's the coherent dipole-dipole and exchange coupling and the hyperfine coupling that is driving that through the coherent Hamiltonian. So one is coherent, the other is stochastic. That's the principal difference. But I agree that they ultimately happen through a triple spin trip.